In this video, we're going to learn how to design and build power supplies. And when I say power supplies here, I'm referring to AC-DC converters. We're going to end up building a 10-volt power supply that is something that you can plug into the mains AC, and then at the output side, it should deliver to you a relatively stable DC voltage. The type of power supply we're going to be building, though, is called an unregulated power supply. What will happen in practice is that the voltage at the secondary side of the transformer inside the power supply will vary a little bit with load resistance. That will cause the voltage to be not so stable. There are ways to fix that, but we're not going to cover those in this video. Let's move on here to the example. We're going to be building a 10-volt DC power supply. It will be able to give us at least 1 watt of output power, and the requirement that I'm going to impose here is that the ripple in the output voltage should be less than 5% at full load. I need to say a few words here about ripple voltage because you might not be familiar with the term. When I say that the ripple should be less than 5% at full load, it means that the peak to peak of the ripple should be less than 5% of the DC voltage. We'll look at a few examples here in a moment, but first I want to show the circuit template that we're going to be using here for our power supply. First of all, we'll be plugging into 230 volt RMS mains. We'll then have a fuse in series with the primary side of a transformer. At the secondary side of the transformer, we'll have a full bridge rectifier followed by our load, which is in parallel with a capacitor. And the reason the capacitor is there is to lower down the ripple. I'll show you how that's done here in just a moment. In one of our previous videos, we looked at full bridge rectifiers. You could hypothetically build a DC power supply using only a full bridge rectifier, but of course you wouldn't really want to have one without a fuse, and the ripple in this case would be 100% of the maximum voltage. You can see here on our plot of the output voltage that the change in the waveform divided by the maximum voltage is just 1. Therefore, the ripple here is 100%. That's bad, and that's why we're going to add this capacitor into the circuit a little bit later. This is approximately what the output voltage waveform will look like with the capacitor in parallel with the load. What we want in this problem is for the ripple voltage to be less than 5% of the maximum voltage. So if this is a 10-volt power supply, then we want to make sure the peak-to-peak voltage of our ripple is less than 0.5 volts. Let's take a look at the other requirement in a little bit more detail here. We're told that the power supply needs to give us 1 watt at a 10-volt load. Let's calculate what the typical value of resistance would need to be. Power equals V squared divided by R. By rearranging the equation, we find that R load equals V squared divided by P. If we plug in 10 volts, which might not always be the voltage by the way, and we plug in 1 watt, then we get 100 ohms. If I were to hypothetically hook a resistor to our power supply with a higher resistance than that, then that would be no problem in terms of the power supply because the power delivered would be less. However, if we were to use a smaller load resistor, then we might run the risk of exceeding the amount of power that our transformer could give us. That's something that we need to be aware of when we choose a transformer. Here are the steps that we're going to follow in designing our power supply. We're first going to choose the transformer. You might recall this particular transformer from a previous video I made on transformers. This is a PCB mounted transformer, and we can see here that the output voltage according to the data sheet is nominally 12 volts. We can also see that the power that the transformer can pass is 1.5 volt amperes. Since I'm designing a 1 watt transformer, this ought to be able to give us the power that we need. We can also verify here that this is indeed a transformer that's been designed to use for 230 volts. You'll find transformers that are designed to be used with 120 volts on the primary side, and you want to make sure that you don't get the two mixed up or you could have a problem. Now that we've chosen our transformer, let's consider how thick the wire needs to be. You want to make sure that you don't have too much current going through thin wires, which could then be a fire hazard. Let's calculate the current that our wiring needs to handle here in our power supply. We know from the data sheet of our transformer that it can pass at maximum 1.5 volt amperes. Therefore, our power supply is going to be able to give us a maximum output power of 1.5 watts. Let's design with this in mind. If I label the secondary current through our transformer here, I can then calculate what the maximum secondary current will be. With 1.5 watt flowing through 12 volts, we find that the maximum secondary current should be 0.125 amperes RMS. About 30 gauge should be fine. So all of the ordinary wiring that we might use here in the lab would be fine for the secondary side of the circuit. How about the primary side? If we look back here at the data sheet, we can see that this transformer is approximately 57% efficient. So let's calculate the power that needs to flow into the primary side in order to deliver the power at the secondary side when it's at its maximum. The maximum input power is going to be roughly the maximum output power divided by 0.57. That works out to be about 2.63 watts. Let's find the current. The voltage at the primary side is 230 volts RMS, and the current that we're expressing here is also going to be an RMS current. It works out to be 11.43 milliamps. These are fairly small currents, so we don't really have to worry about wire gauge much in designing this particular power supply. But if you're designing a power supply where you have to deliver more power, then it's something that you need to be careful about so you don't accidentally start fires. Let's now move on to step 3, choosing a fuse. It's very important to have a fuse somewhere in the design of the power supply. It's very important because if the power supply circuitry were to somehow be short-circuited, then you could have very large currents flowing through the windings of the transformer, burn them out, and start a fire. So we need the fuses there in order to provide fire protection. In this design, I'm showing a fuse over on the primary side, but it's also possible to have fuses protecting both the primary and the secondary sides of a transformer. The maximum current that will be flowing through that circuit on the primary side is only 11.43 milliamps. So let's choose a fuse with a 15 milliamp rating to make sure that we provide protection to the circuit, but avoid nuisance blowing. If someone were to accidentally attach a load resistor to our power supply, but the resistance were too low, then the power delivered would start to grow. The current through the secondary would start to grow, but the current through the primary would start to grow too. So although the secondary side of this particular circuit is not protected, it's effectively protected because any surge of current on the secondary side would cause a corresponding surge of current on the primary side too. If we were going to add a fuse to the secondary side, then we would want to put it right here, adjacent to the transformer, and I think a 175 milliamp fuse in this situation would be just fine. Let's move on to step 4 and choose our diodes. I'm just going to be using standard silicon diodes, but we need to make sure that they can handle the power that would be passing through them. In this particular design, we're not going to have to worry about this too much, but it is important when you have significant amounts of power delivered to the load. For silicon diodes, the typical voltage drop is about 0.7 volts. Let's calculate the power ratings of our diodes by multiplying this voltage drop times the maximum current we expect to be flowing through any of those diodes at any given time. When I say maximum current here, I'm referring to the maximum RMS current and not the amplitude of the current, because I'm trying to estimate the power in the diode. This is an estimate, by the way, because a diode is a nonlinear circuit element. So if I use RMS current, it's not going to tell me the power delivered to the diode. If I use the maximum value of the current, it's also not going to tell me the power burned up in the diode. I'm just making an estimate here. I'm going to be using our RMS secondary maximum current for this estimation. Any standard diode would be able to do that, so this is not a concern here. The last step here in our procedure is to choose the filter capacitor. This is probably the most difficult step. The way this works conceptually is that when the voltage swings high at the input side, it charges up our capacitor. When the voltage then swings low, the capacitor discharges into the load resistor. That's effectively how the ripple voltage is lowered down. If we look here at the graph of load voltage versus time, we can identify when the capacitor is charging and when it's being discharged. When the voltage is falling, the capacitor is discharging. When the voltage is rising, the capacitor is being charged back up. We're going to make a couple of assumptions here in order to simplify our calculations. The first assumption that we're going to make here is related to the RC time constant. Imagine that I have any capacitor and I charge it up to a particular voltage. You might recall that if that capacitor is allowed to simply discharge all the way down to 0, that the discharge graph is exponential. It looks something like this. However, if the time is short, then we can approximate this exponential function by a linear function. In other words, I'm going to assume that this little segment of the exponential graph right here is a straight line. I'm effectively assuming here that all of these discharge time segments are straight lines. This is equivalent to assuming that the RC time constant is large relative to the period. The second assumption we're going to make here is that the ripple is small. This assumption won't be valid if the capacitor is too small. What it effectively means here is that we're going to neglect the time that it takes the capacitor to charge up. I'm just going to assume that the capacitor is discharging from one peak to the next. Let's say that the change in charge on that capacitor from the bottom side of the peak to the top side of the peak here is delta Q. That would be measured in coulombs, by the way. You might remember that Q equals CV in a capacitor. In this case, it's going to be the peak-to-peak voltage that determines delta Q. Delta Q, if we're assuming a linear fall, is also the current times the time. I can write that because of our first assumption. Our second assumption is just that the fall time equals the period. I can relate this period to the period of the waveform that we started off with. It's just 1 over 2f. F is the line frequency, so in Singapore the line frequency is 50 Hertz. In North America, the line frequency is 60 Hertz. The reason for that 2 goes back to the fact that this is a rectifier. The period of the rectified waveform is 1/2 the period of the non-rectified waveform. Let's combine these three equations together. We can set the first two equations equal to one another. We can then substitute in for t from the third equation. We can then solve for c. This equation relates the current, the capacitance, the frequency, and the ripple voltage, or the peak-to-peak voltage here in our output. You'll notice that the ripple voltage is in the denominator. This means that if we want a very small ripple voltage relative to the DC voltage, then we need a large capacitance. So larger capacitors reduce the ripple. In the worst case scenario, we'll have 125 milliamps at the output side. Our line frequency is 50 Hertz, and we want to have a ripple less than 0.5 volts. Keep in mind, though, that our output voltage might not be as low as 10 volts. It might be a little bit higher. For example, if the secondary side of our transformer gives us 12 volts, and then we reduce that by 1.4 volts because of the action of two diodes in our rectifier, we might be down to 10.6 volts at our output side. Do we still want to have 5% ripple? Well, I'm putting 0.5 here regardless because I think it's not going to make that big of a difference. It means that our capacitor needs to be greater than 2.5 millifarads. These are typically electrolytic capacitors, and remember that for electrolytic capacitors, the polarity matters. You want to make sure that the positive side is up here at the top and the negative side is down here at the bottom. Our second assumption is true because 5% is already a small value, but let's check the first assumption to make sure this was reasonable. What is our RC time constant here? Our nominal resistance at the load is 100 ohms, and combining that with our 2.5 millifarad capacitance gives us an RC time constant of 0.25 seconds. Well, our period is only 0.01 seconds, so I think it's safe to say that our RC time constant is large relative to the period. We now have everything in place to go and test out our circuit. Let's go over to the bench and see how this circuit performs. We'll be hooking it up to various loads, and we'll also be testing out different capacitor values. There's one more comment that I want to make about this circuit, and that is the following. Because I'm going to be building this circuit on a small perf board, I'm going to leave off the switch. I'm just going to switch it on over here at the mains. It's not usually a good idea to put a switch right next to a high voltage terminal, for example, on a circuit board, where somebody might go and switch it on and off and accidentally get shocked. We have the power supply built here on a perf board. It's very important not to use breadboards when you're dealing with mains voltages. You can see here on the perf board we have terminal blocks for the primary and the secondary side. We have our fuse here on the primary side, and you can see the 4 diodes here that are used for rectification. On the secondary side of the transformer here, I have a potentiometer. For the moment, the potentiometer is disconnected from the circuit. The first thing we're going to do is power up the primary side of the transformer and see what the voltage looks like after the diodes. We're using the oscilloscope up here to monitor the voltage at the output of our power supply, and we can see that the peak-to-peak voltage is 24 volts. Keep in mind, though, that that's the no-load voltage. That voltage is going to drop when we hook up a resistor to the output. What I'm going to do now, though, is to add a capacitor to our power supply. Right now there's no capacitor on the perf board. I'm going to start off with a 470 microfarad electrolytic capacitor. It is important to keep the polarity in mind, so we want to make sure positive goes to positive and negative goes to negative here when wiring up the capacitor. So I want you to notice what happens to the peak-to-peak voltage as I make the connection here with this capacitor. You can see here that our peak-to-peak voltage is now only 0.4 volts. So even a very small capacitor like this can help our output side, but that's because the load is not attached to the circuit yet. Let's go ahead and attach a load resistor and draw some current from the secondary side of the transformer and see how the performance is. I'm going to go ahead and disconnect this capacitor from the circuit, and I'm doing it very carefully because I know that this capacitor is still charged. Let's discharge it to make sure that we don't have any accidents later. All right, so the capacitor is now discharged. I'm going to make a connection here with a potentiometer at the output side of our circuit. I'm monitoring the current through that potentiometer with the orange multimeter over here, and the unit is milliamps. So right now we have around 13 milliamps passing through the potentiometer or the load. You can see that our peak-to-peak voltage here has dropped just a little bit. We're starting to load down the circuit, and we're going to load it down even more by lowering down the resistance here on the potentiometer. I'm now going to decrease the resistance here at the potentiometer knob. As I start to decrease the resistance here, we're going to draw more current from the secondary side of the transformer through the diodes. Notice that our peak-to-peak voltage starts to change here as I decrease the resistance. I've decreased the resistance so that we're now drawing about 80 milliamps here through the secondary side of our transformer, and that's nearly the limit that we wanted to design this system to handle. So you could say that this is the maximum load or the minimum resistance that our power supply can handle. So we're testing the worst case scenario now. We can see that the peak-to-peak voltage here is 16 volts, but the ripple is still 100%. We've not corrected the ripple. I'm going to add a measurement here to our oscilloscope and measure just the maximum value. At the moment, it should equal our peak-to-peak value. The maximum voltage and the peak-to-peak voltage are equal. That's an indication that our ripple is 100%. I'm going to start adding capacitors in parallel with our load. Let's start off with a 470 microfarad capacitor. Now that's smaller than what we designed for, and I want to show that that's not going to completely solve the ripple problem. We're getting 11.6 volts DC, but our ripple is 1.6 volts. We're at about 10% ripple or so, not quite to what we had hoped to have out of this transformer, but again, this capacitor is too small. Let's use a larger one instead. I've disconnected the capacitor from the circuit, and I want to discharge it here. When you actually use these capacitors in a circuit, it's always a good idea to have a resistance in parallel with the capacitor to give it a discharge path. You don't want to leave any dangerous voltages on a circuit after somebody switched off the power. In this case, if a load is attached to it, then the load itself can serve as a discharge path. I'm now using a 1000 microfarad capacitor. Again, this shouldn't be enough capacitance in order to completely solve a ripple problem. The oscilloscope is not so good at measuring these small voltages unless I change the screen settings, but you can see we're somewhere between 0.8 volts and 1.2 volt ripple. Let's use a larger capacitor. So first I'll discharge this one, and this time I'm selecting a 2.2 millifarad capacitor. I think our ripple voltage here is quite low. The oscilloscope is telling us that it's about 0.8 volts. That's not too bad. Again, I want to discharge this capacitor. Let's try a 3.3 millifarad capacitor. The oscilloscope is still telling us 0.8 volts, but I think this is a problem with the oscilloscope rather than the case of our ripple voltage not actually improving. We can see that sometimes the oscilloscope is telling us that the ripple is about 0.6 volts, which is just about right here. What we've just demonstrated here is an unregulated power supply. If it had been regulated, then the output voltage would have been constant whenever I change the load resistance. We can build regulated power supplies by adding additional circuitry that basically burns up some of the power or has complicated switches in order to make sure that that output voltage is stable. I hope that you've learned the techniques, though, of using transformers, fuses, and diodes for rectifications along with capacitors as filters. Keep in mind that watching this video doesn't make you an expert at building power supplies. Be really careful if you decide to try things like this on your own, and keep in mind that there are additional considerations that you have to make in order to be safe with these circuits. This video is part of an organized sequence where I explore various AC and switching circuits. If you enjoyed it, then you might consider following the channel's playlist to learn more about these types of circuits.